Hi everybody, today I'm going to show you how to design I-beam in the most optimized manner. I have given you some information on top of the I-beam. I means moment of inertia, W is the section modulus, TF is the thickness of flames, TW is thickness of wave, A is the area, and E is the distance from neutral axis to the outer edge of the flames. In case of I-beam, it's the distance from here to here. It's a vertical perpendicular distance. So let's let's start doing some calculation. W is the section modulus. It can be written as I divided by E, and E is the height of the beam divided by 2. Generally, it's the distance from the neutral axis to the edge of the flames. In our case, it's a symmetric section, so this is why it's height of the I-beam, which is indicated with D here, divided by 2. And we all know section moment of inertia, it's BHQ divided by 12 plus AD square. And in our case, first I have calculated this for wave. It's the thickness of wave, which is the breadth in our case, and height is the height of wave to the power 3 divided by 12 plus area of the wave times d square, which d in our case, in case of wave, d is 0 because the distance from the neutral axis to the centroid of the flames is 0. There is no distance between them. It lies in the same point. Both of them lies in the same point, so d will be 0. And in case of flames, there is two flames, upper and lower, so 2 times b is the breadth of flames. Height is the height of flames divided to the power 3 divided by 12 plus area. There is 2 flames, so 2 times b times tf times d square. And since the value is very small because thickness of flames is less than 10 millimeters, so this will not have a lot of influence in the real result. So this is why this can be eliminated. So I will go a bit down. So there I have mentioned the value is not so significant, that is why it can be ignored. So now I will be, like I said before, BHQ divided by 12 plus A, and D is the 0, plus we have ignored this, so we can consider this at 0, 2, and plus 2b times thickness of flames, and D is H divided by 2. And now the equation will look like this. And again, W equals to I by E. I, we've derived the value here, so we can substitute this value over here, and E, which is H divided by 2, and that will give us this result over here. Further, if we would like to derive B, because we know the section modulus when we know the bending moment, that is why we have to look for the value which is unknown, and B is one of the unknown, so I'm trying to find B over here, and when I try to derive B through this equation, this gives me this one, and after that I can have this. And we all know area of I-beam is 2 times the breadth of flames times thickness of flames plus h times thickness of wave, and it will be like this. And when we do the further calculation, this will give us this value over here. And if you have any confusion, you can write me in the comment below, because I've tried to do it as nice as possible. And thickness of wave is height of the I-beam divided by neta. Neta is the factor that I will show you further how it works, where we get this neta factor. But thickness of wave is always always related between the height and the neta factor. It's a factor. I will show you further. And further area can be derived as this one, and when we do the derivative of this equation, AI beam equals to 2W divided by H plus 2H squared divided by neta, the result would be like this. Derivative of this equation is like this, and this way we can get the height equation for the height of the beam, and this is like this. And height of the beam would be like this. Section modulus W we know once we know the moment, and once we know the height, we know the ratio. Height thickness of wave is ratio between height and the neta factor, so that can be derived as well. And we also know the equation B equals to W divided by thickness of planes times H minus thickness of wave times H divided by 6 times thickness of planes. And according to Eurocode, thickness of planes has a relation with breadth of planes divided by 2 times the beta factor. I will show you this beta factor also further when we do the real calculation. And again, B, when we try to eliminate TF here, then TF can be replaced with B divided by 2 times B, and here it is. And after doing all the calculation, B would be looking like this, and we can further to B equals to root under 2 times W times beta factor divided by height minus thickness of wave times height times beta factor divided by 3, and thickness of planes would be B divided by 2 times B. And as we all know, moment is section modulus times Fy, and there will be safety factor lambda MO, and according to Eurocode, lambda MO is equivalent to 1, so that will not have influence in the moment calculation. Fy I have assumed 355 Newton per millimeter square in our calculation, and W would be MED divided by Fy. And this beta and neta factor are chosen according to Eurocode, and in particular this particular example I have taken class 3 beta and neta factor, and I have taken this example from the internet. I did not do calculate it myself. So there is distance between two support is 840 millimeter, load on top of it is 300 kilonewton, and there will be bending moment which is 63 kilonewton meter, and the shear force will be 150 kilonewton. And this is the information about beta and neta factor. And since we have S355, the beta factor BC, and this here it says free A's. In case of I-beam, it's free A's because flange of I-beams are open, so this is why this is open A's. But if we are having box beam, then we have to switch it to this over here, and this is completely different than this one, and neta factor is here. So our material is S355. That is why the neta factor would be 98.9 and the beta factor would be 11.4. And moment
which I took from one example in the internet, is here 63 kilonewton meter. W is the moment divided by Fy, and height is we have derived the equation this earlier, and this is this, where we know W, we know neta, so height will be something like this, and thickness of wave equals to height divided by neta, which will be like this, and B equals to, again, this equation we have derived earlier. You can go back and see how we derived the equation, and it will be like this, and this will be 101 millimeter, and thickness of planes is B divided by 2 times beta factor, and this will be 4.43 millimeter, but we can consider it to be 5 millimeter, and thickness of wave can be considered to 4 millimeter, and height can be 300 millimeter, and breadth can be 110 millimeter, just to be in safe side. And in the same example, shear force is 150 kilonewton, and since we know the shear force already, I'm trying to calculate the area here, and the area we have got 731 millimeters square, and which will be 2 times area is 2 times breadth times thickness of planes plus thickness of wave times height of the wave. And in this equation, I'm interested in height of the wave, because I'm not going to optimize the breadth of the planes, because that would be very complicated to manufacture. So that is why I'm just optimizing the height of the wave. That is why I would like to look what is the required height for the wave, and this gives me the value minus. That means we do not require any height at all, but due to the connection region, because we have to build a connection on the edges, that is why I have considered 100 millimeter on both sides. So at the end, the beam cross section would look like this. We can have constant beam which is going like this, but that is not the most optimized beam, because in that case, even though the beam take all the loads, but still we have used a lot more material than it is needed. Thank you very much, and I will be doing another video concerning the box beam, which should be similar to this one, but in that box beam I will be doing one real example which I have done at one of my work. So thank you very much, and hopefully you understand how the I-beam are optimized.